Similar to LDA and the logistic regression, in SVM, we are looking for a linear decision function. But different from LDA and the logistic regression, we are not going to model any conditional or joint distribution. Instead, we directly model the decision boundary, the linear decision boundary. How we model the decision boundary? For example, in this case, we can use a solid blue line to separate the two groups of points. But we want the separation as wide as possible in the following sense. We can imagine we're going to make some parallel lines of the solid blue line, and we push to both sides until we hit one of the green points, or one of the red points. Meaning we wanted to create a avenue, place an avenue to separate the two group of points, and we want that avenue as wide as possible. And so how are we going to formulate that problem? First, we have to find out a way to formulate those lines. For example, right now for the solid blue line, we have the slope beta and two-dimensional here, in general p-dimensional, and the intercept and beta 0. However, the coefficients beta and beta 0 are not uniquely determined. For example, we can time 100 on both sides, and we get the same line, and we can flip the sign of beta and beta 0, and that's still the same line. And for example, let's consider a two-dimensional x1 and x2, and we have this line. You can parameterize this line as x1 plus x2 equal to 0, or 2x1 plus 2x2 equal to 0, or minus x1 minus x2 equal to 0. They all correspond to the same line. So we have to figure out a way to fix those parameters. Let's first fix the sign, meaning you cannot flip the sign of beta and beta 0 anymore. How we fix the sign? We're going to set the y value, instead of being 0 or 1, we're going to set the y value going to be plus 1 or minus 1. Now, if you are from the plus 1 group, then if I take the x coordinates and plug into this beta times x plus beta 0, that value should be positive. Now, if you are from the negative group, which are the red points, I plug in the x and y coordinates of those red points to beta x plus beta 0, we should get a negative number. For example, in the previous example, suppose my point 1, 1 is from the positive 1 group, then you're going to find out you can only pick representation like this, but not the minus 1, minus 1. Next, we want to fix the magnitude or the scale, meaning we cannot just scale beta and beta 0 by some positive number. How we fix this magnitude? There are 3 lines, the solid line in the middle and the 2 dashed lines on both sides. And then we want to parameterize the 2 dashed lines as beta x plus beta 0 equal to 1 or minus 1. So by doing this, we fix this scale, and so now those lines are uniquely determined. Next, what we want to do is we want to find out how to measure the margin or the width of the avenue. You're going to find out that half of the width of the avenue is actually equal to 1 over the norm of the slope vector. To understand that result, let's first understand the slope parameter when we parameterize a line. For example, let's look at the right. The dashed line is a 45-degree line, and we can represent it by x1 minus x2 equal to 0. So the corresponding slope vector is 1 minus 1. And you can see this is a vector that is perpendicular to the line. So back to our a problem where we have our beta, and we have the 2 lines, the solid line and the dashed line. And so you're going to find out the beta basically is a vector which is orthogonal to both lines. Now, how we find out the weights between the solid and the dashed lines, which basically the length of the red bar, we can just randomly pick a point on the dashed line and let's call it x, and randomly pick a point on the dashed line, let's call it z. And then we draw a vector from x to z. And then to compute the length of the red line, we just need to calculate the inner product or do the projection of this dashed vector onto this direction beta. That can be computed by, just take x minus z and inner product with the normed direction beta divided by norm of beta. Here, the dashed purple vector probably should be represented by z minus x instead of x minus z. But you're going to find out in all my calculation, and what I care is just the magnitude. And so some of the signs may not be right, but we can ignore that because all we care is just the absolute value and whether they are equal. So let's continue the calculation. Now, we just put the norm of beta in the denominator, and the numerator is x transpose beta minus z transpose beta. Well, you're going to find out the numerator is actually equal to 1. Why? Because x is from this line, so we can find out x transpose beta is equal to minus beta 0. And z transpose beta, and z is from this line, so z transpose beta is 1 minus beta 0. So you can find out the difference basically is 1. So we have figured out that if we place a avenue between the two group of points using those lines, and those avenues are parameterized, those lines are parameterized by the slope beta and the different intercepts, and the half weights of the avenue is actually equal to 1 over the norm of beta. So to maximize this is equivalent to minimize half of the beta, half of beta norm square. So this is our so-called max margin problem. When we try to maximize the margin, is equivalent to minimize this objective function, subject to some constraints, because when we formulate this problem, we have to require our points are on the correct side of those dashed lines. And here are some of the constraints, and those two can be written in a unified form, which is this one. Here, actually throughout the whole lecture for SVM, I'm going to use the dot. This is basically the dot product between two vectors. If I'm going to use the matrix notation, this is equal to beta transpose times xi. So this is a problem we wanted to solve. Let me make some comments about this problem. This is a convex optimization problem because we try to optimize a convex function sub and over a convex region. And in particular, the objective function is a quadratic function, and the constraints are linear constraints or affine constraints. And because it's a convex optimization problem, we don't need to worry about local minimals. Any local optimal is going to be a global optimal, which is nice. And further, we know that because it's a convex optimization, any solution of this problem 1 is going to satisfy the so-called KKT conditions. So KKT conditions are going to be both sufficient and necessary. And the last comment is that equation 1 or optimization problem, optimization 1 is a so-called the primal problem. We're actually going to solve the dual problem instead of the primal. So what I'm going to explain in the next couple of slides is the following. The original problem is the primal problem, where we want to solve the slope beta and the intercept beta 0. Instead, we solve is twin sister problem, the dual problem, and where we're going to solve the dual problem and we're going to obtain a bunch of lambda 1 through lambda n. So what are the lambdas? You can think about the lambdas as the Lagrange multiplier from the primal problem, because we have n constraints. So for every constraint, we're going to introduce a Lagrange multiplier, which is our lambda I, from the dual problem. But now the question is how we're going to link the solutions from the two problems. I mean, they're equivalent. It turns out they can be linked through the so-called KKT conditions. For example, once we solve the lambdas, we can use this equality to obtain the optimal slope, which is a solution from the primal problem. How we obtain the beta 0? You're going to find out at least some of these data points xi will have equality and hold. Then we know yi, we know xi, we have already solved beta, so we can solve beta 0. So next, we're going to first introduce the KKT conditions, and then we're going to talk about the duality between the primal and the dual problem.